forward converter is a popular DC-DC, isolated DC-DC converter topologies and based on a single MOSFET. The forward converter is actually a buck-derived topology, and in fact in one of the previous videos we actually derived the forward converter from a basic buck using the basic principles that all isolated converters need to satisfy. In this video we will go through the steady state analysis, including the detailed analysis of the various waveforms of the forward converter. So here is the schematic of the forward converter, and this being a buck derived topology, we expect the operating principles and many of the characteristics to be very similar to that of the basic non-isolated buck converter. In fact, if we compare the topology of the forward with that of a basic buck, we will see that especially on the secondary side the things are very similar. So we have the output stage, the LC filter, this freewheeling diode, identical in forward and the buck, and in a buck converter the input voltage is switched through this MOSFET, whereas in the forward converter it is not directly Vn, but it is actually N times Vn, where N is the turns ratio of the secondary winding to the primary winding, and this is what we use to achieve this voltage matching, which is a big advantage of isolated converters. So for example, if the input voltage is, for example, if this is a step down application, let's say the input is 100 volts and N is 0.1, then we are only switching between 10 volts and 0 on the secondary side, and that is the same as we saw in a previous video. That is one of the main advantages. Okay. So let's focus on the on interval. That's when the switch S1 is turned on, and as seen from this circuit, we apply Vn across the primary winding, and we'll compare the dot polarities of the primary and the secondary winding. We see that the V secondary, the voltage across the secondary winding, is also positive. It is N times Vn, and that will forward bias the diode D1, applying that N times Vn voltage, reduced voltage, to the output stage. Yes, and then the operation is very similar to the on interval of the basic buck converter. Then when the so during this period the power is drawn from the input source, and it is transferred, at least majority of that is transferred through the transformer, through the primary and secondary windings to the output stage. Okay. We will see that there is a small magnetizing current that involves a small amount of energy being stored in the magnetic material. And then when the switch is turned off, for flex continuity, we have this reset winding and reset diode mechanism that will ensure that the flex is continuous. And on the secondary side, again, when we go to the waveforms, we will see that V secondary is actually negative, the diode D1 is reverse biased, and the stored energy in the output inductor, just like in a buck converter, forces the diode D2, the freewheeling diode, to conduct, and so the current, the inductor current, completes its path through the load and this diode D2, again identical to a buck converter. So I mentioned that during the switch on interval, most of the power drawn from the input source is delivered directly to the output stage, and only a very small part of it is stored in the magnetizing inductance, 1/2 Li squared, where I is the magnetizing current and L is the primary side magnetizing inductance. So that stored energy would force the reset diode to conduct as soon as the switch S1 is turned off to maintain flex continuity. So let's just consider the switch on interval. So there are I primary has two components. I primary is the magnetizing current Im plus whatever is the load current component, which we call as I will call this I primary prime. Okay, I primary prime. So and I primary prime is N times the I secondary, and I secondary itself is this inductor current. So the flex produced by, I can also write the flex component as phi in the core to be due to phi m plus the phi primary prime, the flex due to the load current component of the primary current, plus the phi due to the secondary current. Okay. And we know that this phi primary prime exists only to cancel this flux produced by the secondary current, so they cancel each other, and the flux in the core is only due to the magnetizing current component. Okay. And this is what is corresponds to the energy stored, and this is what is responsible for forward biasing the reset diode as soon as the switch is turned off. Okay. So this IM was actually entering the dot at the instant when the switch S1 is turned off. Therefore, what we need is a current that enters the dot when the switch is turned off for flux continuity, and that current cannot be through the secondary side because you need a current that enters the dot, and this diode D1 would prevent the current that enters the dot. So the only possibility is through the reset winding, and here this diode is connected in the right direction that it can support a current that enters the dot. So the current direction is actually current enters the dot here, continues in the reset winding, goes into the input source, and then completes the path through this reset diode. Okay. So what we see is part of the energy that is the complete energy stored in the magnetizing inductance is fed back into the source during the off interval. Okay. We'll see that during the part of the off interval. And it is also important to note that the primary winding and the secondary winding, those are the two main power windings, meaning they carry high current, they need to withstand high voltages. So the VA rating of the two windings is large, whereas the reset winding, the current through this reset winding is very small. It only corresponds to the magnetizing current, and it flows only for a short does not flow for the entire period. So the current rating and therefore the VA rating of this winding is very small. So it does not occupy any significant space in the transformer. Okay, next, in order to be able to draw the various current and voltage waveforms, let's first draw the equivalent circuits valid in different operating intervals, which is decided by the switch and the diode's conducting periods. So during the switch S1 on interval, that's our main power transfer interval from the input to the output. S1 is on, so this is a short. The primary is directly across the input source, and we can see that the reset diode is reverse biased. We can say that because so this end with respect to the ground is at the input voltage, and and from the primary we see that the dotted end is positive with respect to the undotted end. So once again, so the voltage of the reset winding would be positive this side, negative here. So this end is already at Vn, and Vn plus whatever is induced voltage, which is positive, that is going to be the voltage across the reset diode. Okay, so if the turns ratio between primary and reset as indicated here is 1:1, then the diode is reset by 2 times Vn, one Vn here, another Vn induced in the reset winding. Okay, so the point is the reset diode is reverse biased, so it's not conducting, so that is open here. And on the secondary side, we know that, or we can see from the dot polarity between primary and secondary, that V secondary is positive, that forward biases the diode D1, so that is a short. And because of the positive voltage across diode D2, again equal to V secondary or N times Vn, so this voltage here is N times Vn, which is positive, and therefore the diode D2 is reverse biased, and that is shown as open here, and this is the LC filter and the load. So this continues as long as the switch is on. The moment switch is turned off, we enter the off interval 1. So this is slightly different from the buck converter because we have 2 distinct intervals within the off interval. Okay. So the first one is when the core is being reset, meaning we know that at the turn off of the switch we had the flux in the core to be some value. We call that as a phi peak, and that is coming down, and this subinterval lasts till that flux reaches 0. So during this period switch is off, so this is open, and we know that the reset diode conducts, and the reason why it conducts is because the energy stored in the magnetic material would force a current that enters the dot, and the reset winding is the only place where current entering the dot is allowed by the circuit switch arrangements. Okay, so during this period, it is the reset winding that decides the winding voltages, and again we can see that the dotted end is negative with respect to the undotted end. The dot is connected to the negative end of the input source, and the undotted end is connected to the positive end. So all the winding voltages are negative. Therefore, the diode D1 here is reverse biased, and that is open circuited, and the current in the inductor IL would force the this reset diode, the freewheeling diode D2 to conduct, and that is given as a short circuit here. Okay. So because of the negative voltage applied across the V reset winding, the flux in the core continuously decreases at a rate that depends on the input voltage and the inductance of the reset winding, and eventually it will come to zero, and we have to ensure that it actually comes to zero before the start of the next cycle in order for the circuit to be operating in steady state. So the moment that happens, as soon as the phi m in the core becomes zero, that is when we see that that's when we say that the core is completely reset, and then we enter the off interval number 2. So during this interval, operation is quite similar to that of off interval 1, except that the DR is now it is off. The current has was coming down, reached zero, and then once it reaches zero, it cannot become negative because of the diode, and therefore that is also open circuited. Primary switch was already off. The diode D1 was off, and only diode D2 is conducting. It carries the inductor current, and that is shown as the short circuit here. Okay, so we will take up the analysis of the different waveforms in next part of this forward converter analysis video.